Let's move to the subject matter of today, which is the singularity. Okay, and where do we have that? Well, we touched upon gravitational lensing lately, and here you see an example there. And this was done, gravitational lensing was done by mass. Okay, they say mass warps the space-time around it. We forget the word space because that confuses people. We just say it warps time, because that's what they're saying. They're saying that mass warps time, that bends time. And so the photons coming from that far away, that distant star, have no choice but to roll around the warpage created in time. They either roll or slide along that curved surface, and that's why they reach our eyes here on Earth. So you can have an eclipse of the sun, right? The moon in front of the sun, and you can see a star behind the sun, far away, distant star behind the sun. You can see it. Why? Or you can take a picture of it, right? Why? Because according to them, light from that star curved around, slid or rolled along that warped surface which the sun created around itself, right? And that's how it arrives to your eyes. So this one was done, gravitational lensing, that's done with mass. What's the problem? The problem is that we have another similar effect, which is the slit experiment. Okay, and here what you have is this fellow, and his name is Matt O'Dowd. I showed this the other day, and he's got all these particles going through the two slits, and they curve around outwards and inwards and create the pattern on the screen, which are these fringes. And so the question is, how did the particle do that? How do all these particles do that? They just go through two slits, and one goes this way and the other one goes that way. And so they just say, well, according to quantum mechanics, you have Heisenberg's uncertainty principle. And what it does is it doesn't allow the observer, right, us, the person doing the experiment, doesn't allow the observer to know the exact position and the momentum of that particle. And so it could be anywhere, and so by the laws of statistics, one goes this way, one goes that way, and that builds the screen. That builds the fringes on the screen. And so, you didn't explain it physically, you just say it is so because quantum says you don't know the position and the momentum of a particle at the same time. And so that's all they said. It is so. It's because of our ignorance, we don't know. That's all they said. And what's the problem? Well, the problem is that this is how Niels Bohr and Einstein thought about the slit experiment in 1926 during the Fifth Solvay conference, in which they were both members. They came and visited. And let's see if I can get this up here. Here it is. Okay, so this is the illustration by someone, a professor in Canada University, right? And he shows the photon banging against the edge of the slit. Okay, this is a top view, so you can see it bounces inwards. Okay, and because it bounces, it makes these fringes because the balls essentially interfere with each other either constructively or destructively. What's the problem with this? Well, in order to see what the big problem is, we're going to remove the parts of that slit where the photons are bouncing, okay, which is the outer ones. Okay, so we're going to remove both of them. Okay, and here, let me put this up here. And now we're going to remove them. We're only going to read the one in the center. Okay, and we turn that into a needle, so that's why it's rounded. Okay, so we're going to turn this into a needle, and it's a rounded needle. Okay, so that you can see it. And it turns out we can create the same fringes without those two outer partitions of the slit, we can call them, the jam, they call it, the frame, the sill, whatever you want to call that. Okay, so we remove this, we leave only the needle in the center. It turns out we can produce the fringes on the wall without having the photon light, right, bounce against the sill. And so if we can produce it without that, we don't need the slit experiment. We're just going to call it the needle experiment. And we have to explain why the needle experiment also has the particles turning inwards, interfering with themselves, which is what this fellow that we talked about earlier, he cannot explain. He cannot explain how the particles turn inwards. That's the whole issue. I mean, if they bounce against the edges, they will go outwards. And so, what's the law of reflection? Yeah, law of reflection, study it well, bouncing outwards. Law of reflection for particles is bouncing, not always outwards, never inwards. Okay, don't say that they do go inwards, because then you have to explain the process. Okay, so the guy that says it is so, that's all he said. That's his mechanism. Okay, so we have all these singularities that we talked about the other day, and how are they related to the slit and the the gravitational lensing? Well, you have all these entities. They call them black holes, wormholes, Big Bang. Now, that all comes from Euclid's point and line and so on. So all these are done with these singularities. Essentially, the singularity replaced the word point, so-called for the purposes of physics, which it was never physics to begin with. But that's what the word singularity does. It replaced the word point. There's a synonym between singularity and point, because these are non-entities. They are 0D, zero-dimensional, right? No size, no length, no width, no height, no volume, no nothing. Okay. In the case of black holes, they contain a lot of mass. Inside the singularity, we don't know how that is. But the problem here is that in the case of Big Bang, we have that spitting light outwards, and in the case of black hole, it sucks light inwards. And so we have these two singularities, very massive, I guess, singularities, and they work in opposite directions. They work at cross purposes. Big Bang spits, and black hole sucks. That's how I like to present it. Here it is. Okay, there it is. One spits, and the other one sucks. And so, the question is, what do we do with this? How can we explain that? I mean, it looks like, the mathematicians want the best of both worlds. They say, oh, here we're going to have the Big Bang explode, and in the other case, we're going to have it pull. So we have a problem. We have a problem because now we don't know what these entities that the mathematicians invented, how they behave, what to expect. How can you predict anything, which is what they like to talk about, if one sucks all the particles inwards and the other one spits them out? So what's the prediction now? Okay, I want a prediction. They talk about predictions. This is the time that you got to do predictions. Okay? So yeah, we have a little bit of problem here with these folks. A second here, because these people have contradictions in their mechanisms. Okay, and we're going to look at one of those today, which is the Big Bang one. I think that's the big one, because it should have stayed where it was. If it's got all this mass, all this matter concentrated in there, in this nothingness called the singularity, because from there we have all this energy coming out, which is going to convert into matter, then hopefully it was in there somewhere. I mean, how did they create that in there? And that's when all these mathematicians come in and they tell you, let me show you how it was created. Okay, so I want to see how matter was created from the void, just like anybody else. We all want to know this. We want to understand this process. I want to know how God this magic, okay, in his garage. Okay, so here it is. Here's first we need to know what a singularity is. Here's from the National Academy of Science, and says, what is the singularity of the Big Bang? Yeah, what is it? I mean, I'd like to know. How did the universe begin? How will it end? The science. Here's the science. Listen carefully. The Big Bang Theory says that the universe came into being from a single, unimaginably hot and dense point. What was a point? Well, that's the singularity. That's the no size, no shape, no length, width, or height, no mass, no matter, no weight, no nothing, known as the singularity. That's where the universe began. That's the theory, okay? And so they said it didn't occur in an already existing space, because rather it initiated the expansion and cooling of space itself. Okay, so the singularity had no space, no time, no matter, no nothing. From that nothing, space was created, let alone the energy that turned into matter, time, and who knows all the other good stuff that comes out of this singularity. And so we have a problem because they say that it comes from this entity known as a singularity. So we got to get to the bottom of a singularity. Okay, here's the Wikipedia version of this singularity. It says, in mathematics, singularity is a point at which a given mathematical object is not defined. Okay, so what they're saying is it's infinity or infinitesimal or whatever. They use these terms to confuse you completely. And say, and did you understand? Yes, okay, I did. So people just accept it on the basis of authority and democracy. All the mathematicians voted for it, or tradition. You know, we've been doing this for 100 years. Who are you to question us? You know, that kind of thing. Okay, so here's Stephen Hawking. Fortunately, he goes into a little more detail than all these other definitions here. Here he goes. This is Stephen in his own book, his famous book, Brief History of Time. So he says, at some time in the past, the distance between neighboring galaxies must have been zero. So there was no distance between galaxies. At that time, which we called the Big Bang, the density of the universe and the curvature of space-time would have been infinite. Again, that word infinite. Infinite curvature, whatever that means, you know. The density is infinite, whatever that means. Because mathematics cannot really handle infinite numbers, the general theory of relativity predicts, right? We're going to predict the past here, that there is a point in the universe where the theory of itself breaks down. So they predicted that right at this singularity, mathematics breaks down. And so since they can't do any math there, they say, well, at that point we call it a singularity because we cannot go beyond that point. Okay, such a point is an example of what mathematicians call a singularity. All our theories of science are formulated on the assumption that space-time is nearly flat. Okay, so they believe in the flat universe. Forget about the flat Earth. These are flat universes. So they break down at the Big Bang singularity where the curvature of space-time is infinite, whatever that means again. This means that even if there were events before the Big Bang, one could not use them to determine what would happen afterward, because predictability would break down at the Big Bang. Okay, so they essentially, what Steve is saying is that don't ask that question because we have no answer to how the universe came into being. It just did. And we started at a singularity. Don't ask us what was in there, because there was nothing in there. It was zero size, zero volume, no shape, zero dimensions, etc., etc., etc. There was nothing in there. So they're essentially creating something from nothing. That's what they're all about. And Hawking goes in there to tell us how they came up with this nonsense theory, you know, where we end up with this singularity. It's got to do with Hubble. You know, Edwin Hubble, he came up with some measurements out there and says, hey, all the galaxies are receding from the Earth. They're all running away from us today. So apparently they were closer together in the past. How did they figure out that they're running away from us? Well, they have this redshift phenomenon, like the Doppler effect. When it comes towards you, it's blue shifted. And when it goes far away, it's red shifted in terms of light, right? Doppler is really a sound phenomena, but they apply it to light as well. And this is essentially what he says. He says, if the source is moving away from us, the wavelength of the waves we receive will be longer. Longer wavelengths, what does that mean? Well, lower frequency and lower energy, etc. Now, stars moving away from us will have their spectra shifted towards the red end of the spectrum, redshift, and those moving towards us will have their spectra blue shifted. Edwin Hubble worked out the distances to 9 different galaxies, and he determined, right, that most galaxies appeared redshifted. Nearly all were moving away from us. The size of a galaxy's redshift is directly proportional to the galaxy's distance from us. The farther a galaxy is, the faster it is moving away. So, farther away a galaxy, moving faster away from us. It's a hand grenade that just exploded in front of you, right? The universe could not be static. It is, in fact, expanding. Okay, so what they did essentially is run the movie backwards and say, well, if it's expanding and we're getting farther away from all these galaxies, in the past they must have been all closer together. They took it all the way to the Big Bang singularity. They said they calculated it was 13.8 billion years ago, and they said at that point we had a point, a nothing called a singularity, from where this whole process began. That's, in a nutshell, the Big Bang theory. Okay, but we have this fine gentleman, and his name is Krauss, okay? And he came up with an explanation of how the universe sprang from absolutely nothing. And he calls his book A Universe from Nothing. Okay? And so here it is. Here's Mr. Krauss. We'll let him take over and tell us the whole picture of how a singularity gave birth to the universe. Okay? Why we have a universe today, thanks to this big bang that exploded. He starts by defining nothing, and he says nothing, empty space with zero energy. Okay, so we have a definition of nothing. Empty space, right, with zero energy. Well, we don't know what energy is. He doesn't define it, no mathematician ever will. But what do you mean by empty space? Are we saying that space is sometimes empty and sometimes it's not? I mean, without objects in it, what's the difference between empty space and space? I thought space was a synonym of emptiness. So you should just say space with zero energy, or space with some energy, or whatever. But to say empty space, I think we have a problem there, because all he said is empty, Humpty Dumpty. That's all he said. A region of space in which we get rid of everything within it, dust, gas, people, and even the radiation passing through, namely everything absolutely within that region. Yeah, he hasn't explained what it is, because all he's saying is you're going to take everything away that is matter, I guess, and radiation, whatever that is, and he's going to take all that away from a region, and he's going to call that space, or empty space, which, again, I don't know what the difference is between empty space and just space, okay? And he says any fourth grader will tell you how much energy is contained in nothing, even if they don't know what energy is. The answer must be nothing, okay? Great. He's very smart. We can get something from nothing, the ultimate free lunch. Empty space can have a non-zero energy associated with it, even in the absence of any matter or radiation. So the problem here is he says that empty energy with zero energy, but then he says even in that case, when you have empty space, it can have non-zero energy no matter what, whether you like it or not. So there's no such thing. Essentially, he starts out by saying there's no such thing as empty space, because there's always something in there. Okay, it's non-zero energy, meaning it's got something in there which he calls non-zero energy. Great, we learned a lot from him. And of course, we don't know what energy is, because if you look up the word, you won't find a definition for the word energy. In fact, good old Richard Feynman says it's important to know that none of us, the physicists, the so-called physicists, the mathematical physicists, none of them know what energy is. So they can't define it, they don't know what it is, and they can't point to it, and that's what was inside of empty space when the universe started, this singularity. That's how Krauss begins his presentation. Very lousy way to start it. Okay, so he goes in there and he says, virtual particles, particles that appear and disappear in timescales too short to measure. So we have these virtual particles. What are they? Because he's going to use those to talk about this energy that is in empty space that has some energy. It's these particles that are vibrating in there that are going to form this energy. He says, while they are not directly observable, they're not. You cannot observe them, right? No, you can't see or touch them. It turns out that their indirect effects produces most of the characteristics of the universe. Electron-positron pairs can spontaneously appear from nothing for a bit before annihilating each other again. We can calculate the impact on the spectrum of hydrogen of all possible virtual particles that may exist intermittently in its vicinity. Virtual particles, therefore, exist. Okay, so they have these particles. They're just come in for a split second, unmeasurable split second, right? You can't measure them, but they have an effect on real stuff that you can see, and they call those virtual particles. In other words, these are ghost particles. They're spirits. That's what they're using. That's what they're invoking to explain what they observe, what they can measure. And in order to fill in the blanks, they created these so-called virtual particles that just come in for a very brief stay and then go back to being part of space, I guess. Okay, and it says they are responsible for most of your mass and that of everything that is visible in the universe. Virtual particles reflecting the particles and fields that convey the strong force between quarks are popping in and out of existence all the time. Okay, so we have the creation of particles, their existence, they come into existence and out of existence, right? Constantly. And they can't measure them because it's too swiftly for their equipment. Okay? We can calculate the effects of virtual particles on otherwise empty space in and around atoms and the effects of virtual particles on truly empty space. So we have the space around atoms, inside atoms, and then we have the space out there, in the universe. That space, they can calculate the ones close to the atoms, right? Because they can do some subtractions and additions. The problem is when you try to figure out, the energy of virtual particles in space out there, the outer space, right? Particles can therefore carry almost infinite energy as long as they disappear in almost infinitesimally short times. So they're just waving their wands here, their magic wands, and they're saying, look, we're going to do all this by magic. They appear, they disappear. They come in whenever you want, when the mathematicians needs it, because he says, look, we didn't see what caused that, but there was an effect, and we're going to call that unknown a virtual particle, which went back, as soon as we try to measure it, it's already gone. And so we have a problem because they're talking about spirits. They're talking about ghosts, talking about, these weird angels that God sends over. That's what they're doing. They're putting it in the guise of science, physics, when none of it has anything to do with science or physics. This is just nonsense. They're giving you a physical interpretation in which they introduce action at a distance, virtual particles, ghosts, angels, and spirits. They just don't call them spirits because it's taboo. You can't use that word. You have to talk about virtual particles, and that's scientific, because now that's got something to do with quantum. Okay, so here we have, he says the following. He says the positron, he defines it as the antiparticle of the electron. We have a positive electron, which is known as a positron, and a negative electron known as the electron, right? When they meet, when they shake hands, they both disappear. That's the quantum version today. It says the same physics that required an antiparticle for the electron to exist requires one such particle to exist for almost every elementary particle in nature. So everything, a quark has an anti-quark, a proton has an anti-proton, and so on down the line. And when they meet, they annihilate. They both disappear. Okay? When particles and antiparticles meet, they annihilate into pure radiation. Oh, I thought it was space, but they call it radiation. What is this radiation nonsense? Okay, well, that's the energy that is contained within empty space, which was supposed to be completely empty of radiation as well. And so these people are just running around in circles, saying we have these two particles, they meet. One annihilates the other, they both annihilate each other, right? But the annihilation means they turn into radiation, and radiation is this so-called energy that was in the singularity, which is not supposed to contain anything except empty space. And empty space sometimes has energy, which is this radiation. All they did was run around in circles completely. Okay? And so he concludes in his tiny little mind, this great scientist, he says, relativity requires the existence of antiparticles, a demonstration that empty space is not quite so empty. So the guy is going to say the universe from nothing, and he starts with empty space, but then he says that empty space is not completely empty. Okay, so that's essentially his starting point. He says we start with something which we call empty space, but that empty space has this energy, these antiparticles, these virtual particles or whatever in there, and from there we're going to create something. But he's already starting with something. He's not starting with nothing. Okay, so he can't say a universe from nothing. Okay, what all this implies is that for a very short time, so short that you cannot measure their speed with high precision, quantum mechanics allows for the possibility that these particles act as if they are moving faster than light. Okay, so here we get into another one. He says, but if they are moving faster than light, Einstein tells us they must be behaving as if they are moving backward in time. Yeah, all the mathematicians, especially Stephen Hawking, he invented negative time. That means all you have to do is put a negative sign in front of that little t, and you're done. It's such an easy physical phenomenon. Just put a negative T and you're going back to kill your grandfather or something. Okay, so here we have Feynman, and he's going to illustrate what this fellow just said for us. And here it is. He says, if you start out with a single particle and end with a single particle for a short time, there are three particles moving about. You can see there, it starts out with that bottom left one, goes upwards, and at some point they have these reactions in which three particles suddenly exist, and then it continues as one because two of them annihilated each other. Okay, so you have one particle, that's how you started out with, and then you end up with one particle again, but in between you have three particles. And good old Krauss, he tells us, in the brief middle period, for at least a little while, a very tiny, unmeasurable while, something you have spawned out of nothing. Okay, so there's your illustration. You've seen it here for the first time. We created a particle from nothing. That's how they explained it. It says you got one particle, you have another two over here parallel to them, but they have nothing really to do with the first one, but then two of them combined turn into nothing and one continues. So you made particles disappear, and all you have to do is reverse it with a negative T, negative time, and you can stop at the three particle level, and then you created something out of nothing. See how easy it was? Very simple stuff. What don't you understand? Okay, and so here he says the following. He says, just in case, here's a snapshot of how things actually look. He's talking about these virtual particles, right? It's not a real photograph, of course not. Or a movie in this case. I put the movie, but they have he's got a picture in his book, right? But rather an artistic rendering of the mathematics governing the dynamics of quarks and the fields that bind them. Okay, so they have these, that you're staring at virtual particles there, and you can see they're disappearing and appearing constantly from the void. Supposedly that's what makes up this region of empty space. And I haven't seen it empty yet, but I won't hold my breath, right? The odd shapes and different shadings reflect the strength of the fields interacting with one another and with the quarks inside the proton, as virtual particles spontaneously pop in and out of existence. So there you have it, folks. You have all this popping in and popping out. Those are the virtual particles that make up space, which is empty of everything because we removed even radiation from it. Virtual particles, whatever energy, field, whatever you want to think of, it's out there. That's called empty space. But then they say, well, empty space contains all this garbage in it. So he doesn't start from absolutely nothing as he falsely advertised. He starts with something. And that something is this energy, whatever it is, because that's undefined, and this energy is a bunch of virtual particles that annihilate each other and turn into something, and from something to nothing and back again, and so this is how he starts a universe from absolutely nothing. Okay, and that's why we like to define these terms before we can make sense of what good old Krauss came up with. Okay, good old Larry. Okay, so here he is. He says, by measuring gravitational clustering, this is another version of that, and now we're going to talk about relativity here. It says, observers have been able to confirm a flat universe. Okay, again, we have this flat universe in which we live. It wasn't flat Earth, but yeah, if it's a flat universe, I guess the Earth is flat as well, in which the dominant energy resides in empty space. So we have empty space, but we have this dominant energy residing in it, inhabited the empty space, and in which everything we can see accounts for less than 1% of the total energy. In other words, the stuff we see, that's 1% of the stuff out there, and the rest of it is hidden in this dark space, which is empty, which is really filled with energy. That's the starting point. With the matter we can see being composed mostly of yet unknown new type of elementary particles. Yeah, so they're gonna create these new particles that have to be there, and they're looking for them. They say it's got to be all this matter in this dark world, and we just have to look for it. We have to identify these particles. How are they going to identify the particles if they're invisible and intangible? Okay, that's the issue. And the way they're going to do it is through experiments looking at the visible stuff. And so we've got another million years of research ahead of us. You know, they have job security because they've created a monster. They said, we're going to figure this out through experiments and measurement, but they're only going to measure the visible stuff and indirectly infer, right, what moved it or what caused the phenomenon. And they're going to give names to those unknowns, and they're always going to tell, well, we don't know really what it is, but we're still investigating. So he says 99% of the universe is invisible. Yeah, tell me about it. 1% visible matter embedded in a sea of darkness, matter surrounded by energy in empty space. So all he said is absolute nonsense, because he's not talking about nothing. He's talking about empty space being nothing, but that empty space contains energy and particles and annihilations and who knows what else, fields, you know, and mass, and it's got nothing in it. And from there, he's going to start the universe from absolutely nothing. And that's how they do this singularity. They say, you know, singularity gave birth to everything. Singularity is nothing, but it's got all this energy in it. Okay? The flat universe is approximately 70% dark energy, a flat universe with 30% of energy in matter and 70% in empty space, which is what? A bunch of energy. Okay, the origin and nature of dark energy is without a doubt the biggest mystery in fundamental physics today, and will be forevermore, because they're never going to figure out what this energy is, let alone dark energy, let alone if they're going to say that it's empty space full of dark energy. We have no depth understanding of how it originates and why it takes the value it has. We have no idea why it has begun to dominate the expansion of the universe. And this fellow is teaching us, trying to teach us, trying to give us this theory that the universe came from absolutely nothing, from a free lunch, as he calls it. Yeah. So let's summarize good old Larry here. Just a quick summary. He says, nothing, empty space with zero energy. That was his definition of nothing. But then he says empty space can have non-zero energy, even in the absence of matter or radiation. Meaning whether it's got matter or radiation, which is what they really refer to when they talk about energy, right? And so it's got energy even though it has no radiation, right? And electron-positron pairs can spontaneously appear from nothing. Dark energy resides in empty space. Okay, so what have we learned? We learned that nothing is something. And from that nothing, that something, right, he's going to come up with something. Great. You know, he must have broken his head on this one, you know. Okay, so this is Bill Gaede's version of this, okay? And we go back to the singularity. That's why we need to define these terms. And, yeah, this is his concussion, his conclusions, right? A singularity is a nothing that only contains empty space, time, potential matter, radiation, energy. And I didn't list all the other stuff that it's got in it. I'm sure it's got fields, and he didn't talk about that, but I'm sure he's got a lot of more stuff in there, mass and who knows what else. And when you look up the notion, the definition we have of singularity, right, what you find is what you find on the right there. It's got no length, width, or height, no shape, no size, no volume, radius, diameter, matter, mass. It's got absolutely nothing. And that's what a singularity really is as defined by them. But then, you know, he puts all this stuff into that empty space, into that singularity. And he tells you in your face with a straight face, he says, the universe came from absolutely nothing. How did it do that when you fill that nothing with so much garbage? You know, and this is where their contradiction is. And they'll never solve that. Mathematicians have no way of solving it. Why? Because they do not do physics with objects, with things. They want to do it with numbers, with equations, with experiments in which they're trying to touch and see that which is, you know, intangible and invisible, right? And so they think they're going to solve it through experiments and equations. This is an issue where you sit back, put your feet on your desk, at home or in your office, have a beer, and you think. Put two fingers on your nose like that, and you think until you get it right. And then you'll understand the universe.